So today we're going to look at chapter 1, basic concepts. The learning objectives for this chapter is basically for you to be able to explain the basic concepts in engineering circuit analysis. So the module objective, that is also the objectives for today. The first is to use SI units and prefixes. Second, explain the basic circuit elements and electrical quantities. The third is to explain the independent and dependent sources. And the last topic is to calculate the power absorbed by a circuit element. So the first topic is about SI units. So there are only a very limited numbers of SI base units. So we have learned the base unit of length, which has a unit of a meter. And the mass, we learned that from the previous physics course already. So that has a unit of a kilogram. Time has a unit of a second. Electrical current has a unit of an ampere. We use the letter A to represent the current unit. And this is also the only SI base unit defined for circuit analysis. So I think the first quiz question that you saw is about this, right? So what is the SI base units defined for circuit analysis? Thermodynamic temperature has a unit of a Kelvin, and the amount of a substance have a unit of a mole, and the luminous intensity have a unit of a candela. Electrical current is the only one that is defined for circuit analysis. So it also implies that all the other units can be derived from all these existing units. And sometimes for very large or very small quantities, we need to use SI prefixes together with the base unit to define some quantities. The SI prefixes include these many, so you don't really have to memorize all this, but it's better to know some of the common use ones. For example, tera, which is a 10 to the power of 12, and the giga 10 to the power of 9, and a mega 10 to the power of 6. So I still remember, like, from about more than 10 years ago when I started undergrad study, and at that time we used a floppy disk. So I remember at that time, like, we used kilobytes to describe the memory, and over time we start to switch to like the some disks or USB drives, and we have like have a memory of megabytes, and later on we have a like even very small USB drive that has memory in gigabytes. And now, like in our computer, actually for my own desktop, I got a like 1 terabyte hard drive. These few over here on the other column, which are in smaller scale, these are also very commonly used. For example, 10 to the power of -3, that's a milli. 10 to the power of -6, micro. 10 to the power of 9, this is nano. And 10 to the power of 12, that's pico. And these few are not very commonly seen in at least in circuit analysis. Most of the time, we don't really need to use the quantities in that level, at least for this class. So we talked about the SI base units already. Here is the list of derived basic electrical units. So these are all the units that we will see from this class. And the first is power. Power has a unit of watts, but this unit is not a SI basic unit. So it's a derived unit. It can be represented by those SI basic units. So 1 watt, that is equal to 1 meter square kilogram second to the power of -3. So of course you don't need to memorize this correlation. So this watts is the unit that we use, and it represents that, you know. And the second very important quantity is called electrical charge. Has a unit of a coulomb. The next concept is the electrical potential difference. So it has a unit of volt. So if you ask your friend, what is the electrical potential difference of a battery? He might be confused. But that is the correct term. So most of the time we say voltage. So for regular AA battery has a voltage of 1.5 volts. The capacitance has a unit of farad, and the electrical resistance that has a unit of ohm. Electrical conductance is basically the reverse of the resistance. So the resistance talk about how much it resists current flow, and on the other side, electrical conductance talk about how it facilitates current flow. So Siemens has a unit of, it has a symbol of S. The magnetic flux has a unit of Weber, and the magnetic flux density is Tesla. The inductance has a unit of Henry. Let's look at the basic circuit elements. So we only have 3 basic circuit elements. The first one is a resistor. Oh, resistor have a symbol like this. So it has this zigzag pattern. It represents that it will resist current flow through this element. So the second one is a capacitor. So there are many different types of capacitors. And some capacitors, for example, this is ceramic capacitors like this. So they don't have a polarity. You can connect it to the circuit like in either ways. You can connect this way, you flip it, it doesn't change anything. But there are also capacitors that have the reference polarity. So you can only connect those capacitors in one way. If you put it in the other way, it will explode. I'm not sure whether you have experienced crack open any of these before. So if you open the case, you will see some fluid, and at the same time you will see like it's a coiled film. So you will see you can explain it. Actually, it has a very large surface. So the symbol for a capacitor is something like this. So in some textbooks they use a capacitor. They tell the difference between the capacitors. Sometimes they use this symbol to represent a capacitor with a reference polarity. So one side is positive, the other side is negative. And normally if they do that, they will label the plus and minus sign on both sides. So in this class, we don't differentiate them. So this is one way to draw a capacitor. A second way, you can also do it like this, just by having 2 plates, but without having the curved side. So this is also fine. You can draw the capacitor like this. So next one is the inductor. So inductor is also a very common element in any circuit. And actually you can make these conductors pretty easily by wrap these copper wires around a cylinder, that you pull it out and it becomes an inductor. So this is why the inductor also have a symbol like this. It looks like a coil, right? So these 3 are the basic circuit elements. Let's look at the basic electrical quantities. The first one is charge. So charge talks about the quantity of electricity. So how do you describe how much electricity we have? Charge have a unit of coulomb. We talked about that already. 1 coulomb is equal to 6.24 times 10 to the power of 18. The second quantity is called current. The current talks about the flow rate of a charge. So how fast the charge flows through an element, that is called a current. Current have a unit of amperage. We use a symbol A to represent that. So there are AC current, there are DC current. The AC current represents an alternative current, so it changes in time, and the direct current doesn't change over time. So from the definition, we know that the current I, so normally we use the symbol I to represent a current. Current I is equal to the rate change of a charge, so that is dq over dt. And a voltage, that is the electromotive potential difference. It also describes the energy needed to move 1 coulomb charge between 2 ends. So it has a unit of V. So from the definition, we know that voltage that is equal to dW over dQ, and W over here that is the energy, because voltage talk about the energy needed to move one coulomb charge. Q is the symbol that we use to describe the charge, to move one coulomb charge between two ends. So this is the definition of voltage. And the next one is the power. The power is the energy rate. So either one element absorbs or release energy, doesn't matter. So the rate of that energy change is called power. Power have a unit of watts and with the symbol of W. And from the definition, we know that a power that is equal to energy rate, dW over dt. Next topic is the basic electrical quantities. So the first is notation of a current. So how do we describe a current in a circuit? So we use the arrow to indicate the reference direction. For example, in the first case, we use this arrow over here to describe the reference direction of a current. So it doesn't have to be the physical direction of the current. So that is just a reference that we use to describe the current, how the current flows. For the same current, if I draw the reference direction point towards the left, this I1 will be equal to negative 2M. If the initial and the terminal node are labeled, we can use double index notation. For example, we have a current over here. I flow from the node A to the node B, and we can define the current as IAB that is equal to 1 amp. So that is how we define a current. And you can also put the current next to the branch and label it with a number. So this is 0.5 amp. And you can also use this to represent a current, say I1, by using the numbers as subscripts to describe a current. And over here, we need to pay attention to the number that we use here. If we pick a reference and we have a current that has a negative number, it just means the actual current is in the reverse direction of the reference. So basically means in this circuit, the current goes through this branch. It's a 3 amp to the left. But to make it easier to remember, you can always use a reference. Say the current is going to the right, but it's a negative 3 amp. That is also fine. So that makes it a little bit easier. We use the arrow to represent the reference direction all the time. Yes.
Does that mean for circuit 2, if I change the direction of the arrow or the current, I would change the sign?
Yes.
Current?
Yes.
Okay, thank you.
Next is the notation of voltage. So how do we describe a voltage? So voltage that talks about the reference, the electrical potential difference, right? So this is why we need to define the reference polarity. We use the plus and a minus sign to define the reference polarity. So in this case, if I put the plus sign here and the negative sign over there, it means the electrical potential difference between A and B, or you can say A with respect to B, that is equal to V. So it means that. It means how high of this electrical potential of A compared to B. So this is why we need to use the plus minus sign to define the reference polarity. Now on top of that, we can put a value over there to represent like what's the difference. So we can write it as V1 is equal to 2 volts. It means that A is higher than B by 2 volts. You can also say that the voltage between node A and B that is equal to 2 volts. We can also, in addition to use the numbers, we can also use the nodes to label the voltage. We can label it as a VAB, means that A with respect to B that is equal to negative 5 volts. So similar to what we had for the current, if we have a negative number, it basically means in reality, B is higher than A by 5 volts. So the next is our current, the power sources. So this topic I talk about independent and dependent sources. So we only have 2 different independent sources. So one is called a voltage source. The voltage source have a symbol like this, and it has a plus minus sign there. So it tells you that this top side has higher potential compared to the bottom side. Besides that, we will give a symbol for this voltage source, or we can write the voltage difference here with the numbers. That is also fine. So this is a voltage source. The other independent source is called a current source. It has a symbol like this with an arrow in the middle. It tells us that the current is always flow in this direction. In addition to that, we have either a name over here or tells like what is the current in numbers. So either way is fine. So we only have these 2 different independent power sources. It also implies that we have 4 different combinations of dependent sources. By looking at this source, on the right hand side, we know that the output will be a voltage. And at the same time, this voltage depends on another voltage. And this relationship is V that is equal to coefficient mu times the Vs. So Vs is over here. So this is also called voltage dependent voltage source. And then similarly, on this side, it has a current output. And this current depends on another voltage by a coefficient G. So this is why this source is called a voltage dependent current source, because it is a current source. Look at the symbol. So that all the dependent sources, they use this like diamond symbol to represent this is a dependent source. Similar to that definition, we will be able to call this as a current dependent voltage source. It depends on this current Is, right? And this will be current dependent current source. Next topic is how do we calculate power observed by a circuit element? And to do that, we need to learn what is the convention that we're going to follow to describe the voltage and also the reference current. So this is called a passive sign convention. So in passive sign convention, we assume this element is a passive element. A passive element means that it only absorbs energy. For example, this resistor here, that is a passive element. So when there is a current running through, or you apply the voltage on the 2 ends, and it will generate heat, right? So it absorbs the energy. So in this passive sign convention, the power received is positive, while the power supplied is considered negative, right? So we need to define the passive sign convention by following what we have here in this picture. So if we define the reference polarity for the voltage as this, left-hand side positive, right-hand side negative, we will define the reference current flow from the left to the right. So in this case, if both are positive, it means that the higher voltage on this end, low voltage on this end, and the current flow from the left to the right, so it means it absorbs energy. The power is also positive. And the other way, if we have this voltage reference polarity and with the current flowing to the left, it's not following passive sign convention.
Does that mean that when current flows from plus to minus, that power is received? And then when current flows minus to plus, that power is supplied?
I would say don't try to judge it that way, so that makes things over complicated. Always follow the passive sign convention, you won't have any problems. If you follow passive sign convention, if it's a positive, it means that it absorbs energy. So these are all defined by yourself. You define what is the reference polarity, you define what is the reference current. So we'll have examples on that. Then the next question is about how do we calculate power absorbed by a circular element? Why I say absorbed? Because we follow passive sign convention, right? And if we get a negative number, it means it's not absorbed. So from the definition, we already learned that the current is the charge rate. So dq over dt. dq is the amount of electricity and per unit time. So that is the flow rate, right? So that is the current I. And voltage is the energy needed to move one column of charge. So that is dW over dq. And the power, that is the energy rate. So W is the energy, dW over dt. And from that, we can calculate the power. We put the power over here. Power that is equal to dW over dt. And at the same time, dW, we find dW can be calculated by using V times dq, right? So we put a V times dq over here, we copy the dt over. And dq over dt, and it becomes current, right? So this is why we can also calculate the power by using the voltage times the current. And remember, we are going to use the passive sign convention for that calculation. And in this example, let's take a look. For this element over here, the reference polarity for the voltage, that is the positive on the top, negative on the bottom. And following passive sign convention, we need to define the current flow from this end to the other end. So this is current I, and this voltage is 3 volts. They follow the passive sign convention. So this is why the power that is equal to 3 times 2, that is equal to 6 watts. And we also know that it's positive, so it means that it absorbs energy. We can also say it absorbs energy at a power of 6 watts. Let's look at a second example. For this element P1, and this is the voltage reference polarity, and this is the current reference direction. So we know that it flows from the high voltage end to the lower voltage end according to the definition of a reference polarity. So it follows the passive sign convention. And if we know the voltage is 4, current is 2, so we can find that the power is 8 watts. So this element is a passive element. It absorbs energy at a rate of 8 watts. And how about we calculate the power on the other side, on this element? This doesn't need to be an element. It can be the whole big chunk of the rest of the circuit, right? So we look at one element in the circuit, and we look at what happened to the rest of the circuit. So let's call this big portion as a P2. And if we define the voltage reference like this, we use V1 as the voltage that is equal to 4 volts. And to be compatible with the passive sign convention, we will need to define a current flow from the top to the bottom, right? So this is how the current will flow, right, through P2. And this current is in the reverse direction of this current I. Do you see that? This current basically goes this way. But this current I, that is the same current, but it's defined to go this way. So that we know this current I2, the current that I define over here, that is equal to negative 2 amp. So I can use the passive, the power calculation. This is 4 volts times negative 2 amp, that is equal to negative 8 watts. So we know that in this circuit, P1 absorbs energy at a rate of 8 watts, and P2 supplies energy of 8 watts. So that makes sense, right? For the whole circuit, one element absorbs 8 watts. The rest of the circuit has to supply 8 watts. Otherwise, the energy won't be balanced, right? So if we add all the power absorbed by all the elements in the circuit, in this circuit we have 2 parts, P1 and P2. We add them together, it'll be 0. So this is also summarized in Telegreen's theorem. It says that the summation of the powers observed by all elements in an electrical network is equal to 0.